Right. Moving on to our analytic tree. First one we want to do is look at verifying identities. So using trigonometric identities to simplify expressions or to verify an equation. And the best way to do this is just to jump right in. When verifying an identity, right, the goal is you start with one side and you just continue to work algebraically to get to the other side. It does not matter which side you start with, either the left or the right. Start with the left side. Generally speaking, when you don't know what to do, just try reducing the problems to sines and cosines. So we know that secant is 1 over cosine. We know that cosecant is 1 over sine. If you hit a roadblock, try starting with the other side. Generally speaking, one side is going to be easier to see than the other. So maybe you may get to this point and not know how to continue. Try starting with the other side. But if you're really clever, and if you're familiar with the techniques of math, rewrite 1 for Pythagorean identity. Sine squared plus cosine squared equals 1. So I can just replace 1 with sine squared plus cosine squared. And then realize, oh, well, split down the 2 fractions. That first term, you get sine squared over sine squared, which is 1. Second term, you get cosine squared over cosine squared is 1. Left with 1 over cosine squared plus 1 over sine squared. One over cosine is secant. 1 over sine is cosecant. which is what we are working towards.
No, it's starting from the left side, If it goes from the right side.
Follow what I just did in reverse. And if you follow that, you see that that would actually have been easier to see where it progressed, right? Because eventually we've gotten to the sine squared plus cosine squared over, which is clearly 1. And from there you're done. There is a third method. I guess technically it's a second method, where you just simplify both sides and show that they reduce down to the same thing. And so if you wanted to just reduce both sides down to sines and cosines to show that they ultimately reduce to the same thing, which would have been 1 over cosine squared sine squared. So there's more than one way to do it. Which technique do I want to use here? Maybe put this one. Start off from the other side. Notice you can factor out a tangent squared. So do that. And remember what your goal is, because you know what you're aiming for. Is there an identity that relates tangent to secant?
Tangent to secant.
There is one.
Tangent is equal to sine over cosine. That one?
I mean, you could use that
That one is a fundamental.
to try to proceed from here, but there is an easier way.
1 plus tangent.
Yes.
To equal 0.
1 plus tangent squared is secant squared. Well, there's a tangent squared plus 1, that's secant squared. In that Pythagorean identity, solve for tangent squared. Secant squared minus 1, right? So tangent squared becomes secant squared minus 1. Tangent squared plus 1 becomes just secant squared. Now distribute that secant squared through. Secant to the fourth minus secant squared, which is what we were after. Let's make these a little more cheerful. So we're happy we got them. And what I want to proceed. I mean, if you look at this, what do you think to yourself? It's easier to start with the right-hand side here. Because you know how to simplify fractions. But I'm going to start with the left-hand side. Because doing so will allow me to show another trick that is often used. First, just write that in terms of sign, right? Cosecant 1 over sine. But look what you're after. You want a 1 plus cosine in the denominator. Two things you can always do in math. Multiply by 1 and add a 0. 1 plus cosine of 1 plus cosine, isn't that 1? All I did was multiply by 1, which does not change your value. Right? 1 times anything is itself. Here's another common trick. 2. Two same as 1 plus 1, isn't it? So I'm just rewriting 2.
What's the point of doing that?
Because it's going to help me get to where I want to be. I have a 1 plus 2 cosine of x. Almost at a perfect square. Cosine squared plus 2 cosine of x plus 1 would be 1 plus cosine of x all squared. Rewrite one of those ones. Sine squared plus cosine squared. Addition of real numbers. There's two very fun properties. It's commutative, and the order in which you write it doesn't matter. And it's associative. How you group doesn't matter. And so it's going to group all the cosines in that one together. That gives me this is a perfect square binomial. One plus cosine all squared. And again, remember the order in which you write doesn't matter. So you would take write this what, cosine plus 1 all squared, but just with the order. You're allowed to do that as addition. And then it's attached by addition. Write this as two separate fractions. Simplify. So the first one would be, right? Sine x over 1 plus cosine. Second one. One plus cosine, and then over sine, right? Which is precisely what we wanted. Again, if we were to start at the other side, because it's the easier one to see, you can see that we'd just be going in reverse, wouldn't we? This would be the first thing you do. Common denominator. this. Expand this out. Cosine squared plus 2 cosine plus 1. Sine squared plus cosine squared is 1. 1 plus 1 is 2. Factor out the 2. Cancel. 2 over sine is 2 cosecant. And just with that, you wouldn't have had to worry about any of those tricks. Another technique that is not often used is to show that the difference of both sides is 0. So you can show they equal 0 and they have to equal each other, right? So that is another technique that can be used. It may sometimes be easier. I think in this case it's easier to do it this way. So this is actually now what we're working towards. So that difference is 0. Adding two fractions, you have to find the common denominator, right? Just a product. In that first fraction, we need to multiply by 1 plus sine over 1 plus sine. Second fraction, you need to multiply by a cosine. And cosine over cosine. For that first fraction, isn't that a difference of squares? One minus sine times 1 plus cosine. And then cosine times cosine. Write that as a single fraction. Factor out the -1 from those last two terms. But what's sine squared plus cosine squared? It's 1. You get 0. Which is what we wanted. Which side of it's easier to start with?
Maybe the right one.
You want to start with right?
No, I don't know. You ask which one is easier.
So start with right. How do you want to proceed?
We could use the Pythagorean identity. 1 plus 10 squared equals secant.
Problem is, there isn't 1 plus tangent squared. There's 1 plus tangent.
We can use then sine or cosine.
And when in doubt, write everything in terms of sines and cosines. But now what? So I'm going to leave that there. I duplicated it. Let's show you. Start from the left-hand side, see where that gets us. Probably want to start the same way, right? Right, in terms of sines and cosines. Which is going to work out nicely. Where do we go from here? No, I've already written the right-hand side in terms of sines and cosines, right? We want sine A over cosine A minus 1 in the numerator. We want sine A over cosine A plus 1 in the denominator. Why don't you just multiply everything by sine? Multiply by 1, right? So you're not changing anything. What's 1 over sine A times sine of A? It's 1, right? Uh-oh. I don't want to go to the next slide. Oh. You're essentially done. Call that right-hand side. Call that left-hand side. They produced the exact same thing, didn't they, in terms of sines and cosines? So you just showed that the right-hand side and the left-hand side are the same. You're done. That was that second technique I told you about, where you just reduce both sides and show that they ultimately go to the same thing.
This technique is the best.
Yeah, it depends. I never use this technique. I always just like to start with one and work my way to the other.
So it depends on what.
Depends on you.
I mean,
Which technique do you want to use? Right, in this case, you kind of got stuck, starting with the one side, so go to the other side and see what happens. And you can see that you can get to the exact same thing, so I mean, maybe that's where you just go, okay, well look, I got the same thing on both sides and done. But it's really up to you how you want to proceed. The one thing you can't do is assume that the two sides are equal and try to reduce from there. So you can't do that. Other than that, it's fair game. You also can't show it's true for just one value. Like you can't say, oh, let's just let A be pi, or something like that, and show that, oh, look, the two sides are equal. All that does is show, oh, well, for that specific angle, they're equal. Doesn't say anything about, okay, well, what if it's a different angle? What about pi over 632? Or is that equation true for that angle? If it is, well, I'll just come up with another angle. So you have to show it's true for every possible angle.
I have one question from the last one. So the key in this one was multiplying everything by sine over
Sine over sine.
That was the key.
And again, since we already did this, you kind of already knew that that's probably what you should do, right? What side do you want to start with?
And the first step and the left one.
Left. The first step should be fairly obvious. Write tangent as sine and cosine. You should already have sines involved, so you might as well just make everything in terms of sines and cosines. What is tangent in terms of sine and cosine?
Sine over.
But what do you notice? What should you notice immediately now?
There are two fractions.
Well, that's definitely true.
Okay.
Ignore that for right now. We'll deal with that. Don't you have a common factor in the numerator?
Yes.
Factor it out. you should notice you have a common factor in the numerator and the denominator, right? Cancel that factor out. Now what do you want to do?
One more cosine is equal to secant.
I think there's going to be a problem with that right now, though. Maybe not. Yeah, that might cause an issue. So what I would do is, right now you're kind of dedicated to keeping everything in terms of sines and cosines, keep it that way. Let's deal with that. You pointed it out earlier. Compound fraction. How do you get rid of a compound fraction? There's technically two ways to do it, but I'm going the easiest way. Look at every single term. If you have 1 over cosine, you have 1, and you have sine squared. What is the LCD? So what's the denominator of your first term? Cosine, right? What's the denominator of 1? 1. What's the denominator of sine squared? 1. You want the least common multiple of them. That's your LCD. Well, that's easy. It's just cosine. So your LCD of all the terms is cosine of x. Multiply both numerator and denominator by the LCD. That's how you clear out a compound fraction. So what we're going to do is multiply by cosine over cosine. And note, that's just 1, so we're not changing the value. bunch of cosines, can't you rewrite sine squared in terms of cosines?
That would be 1 minus cosine.
1 minus cosine squared, right? But 1 minus cosine squared is the difference of squares, right? One plus cosine times 1 minus cosine. Isn't there a common factor?
Yeah.
1 minus cosine, 1 minus cosine. But product of fractions, you just multiply straight across. Can't we write this way? One over cosine times 1 over 1 plus cosine. What's 1 over cosine?
Secant.
Isn't that what we want? And so you don't. Yeah, this one. This one has an obvious starting point. Start with the left-hand side. best option. Write everything as sines and cosines. What's cotangent?
Cosine inverse.
What's tangent?
Sine inverse cosine.
What's cosecant?
Co inverse.
What's secant?
Inverse cosine.
Let's see how I want to proceed. Let's do it this way first. Just multiply through in the numerator. Cosine times cosine over sine, cosine squared over sine, right? Sine times sine over cosine, sine squared over cosine. It's a compound fraction, isn't it? What's the LCD? So go term by term. How many fractions? There's 4 total terms, right? Start the numerator, left-handmost term. What is that denominator?
Sine.
All right, second term, what's the denominator?
Cosine.
Third term, what's the denominator?
Sine.
Fourth term, what's the denominator?
Cosine.
What's the least common multiple of sine and cosine?
Cosine.
It's just their product. Sine times cosine. No, it's just sine times cosine. Whatever that happens to be. That's the LCD. So multiply numerator and denominator by that. What are we going to be left with? Cosine cubed minus sine cubed in the numerator. Right? Over cosine minus sine. Now look at the numerator. There's not a difference of cubes. What's the difference of cubes formula? So I'm going to use that. Don't stick the annotation probably cosine times sine. That matters. It was a common factor, right? Addition, commutative, and associative. There's a cosine squared plus a sine squared. That's just one, isn't it? Multiplication of real numbers, isn't that also commutative? The order in which you do the multiplication doesn't matter, right? Cosine times sine, the same as sine times cosine. No. Isn't that what we wanted? Very common question that's asked, right, is how do you know to do that? It was asked today, right? Let's go back to it right here. How do I know the right 2 is 1 plus 1? You're not going to like the answer. I've been doing math for over 30 years. That's how I knew. How do you know what identity to use? You just have to do them enough. Right? I can teach you the identities. I can teach you the strategies. In terms of doing actual verifications, I can't teach you that because each problem is different. So I can show you a problem and tell you and go over how to do it, but that's not going to be the same for them the next problem. So you're going to have to do a lot of these until you start to see these kinds of things. Like, when would it be best to write everything in terms of sines and cosines versus not? When do you apply each identity? So you're gonna have to do a lot of these. Where do we want to start? Now what do we want to do? Yeah, this is sadly one of those where it doesn't matter which side you start with. So you don't see what to do, you're never going to get there. Now, if you're starting with the left-hand side, that means you want to work towards the right. The right-hand side has a cosine alone in the denominator. So just try to multiply by cosine over cosine and see what you get. Don't bother distributing the denominator. Our goal is to try and get that cosine alone. So there's no point in distributing it. A little bit of rearranging. Maybe I don't need to rearrange just yet. Notice what I did. I just added 0, didn't I? With a +1 and a -1. Any number plus 0 is itself. So adding 0 doesn't change the value. But what this does allow us to do now, 1 minus cosine squared is sine squared. This direction is definitely a lot tougher to see than the other direction. I want to add 0 again. I'm also going to rewrite. That's sine squared theta out in front. Plus the sine theta cosine theta. That's where I'm going to add my 0. I wonder if maybe it would have been better. This is probably one of those cases where it's better to try and do left-hand side and right-hand side separately. So after I finish this up, I'm just going to go ahead and do that. Because this part is not obvious. That numerator factors that. second. I'm going to need to restart PowerPoint. Right, once you see that factorization, you're done. Like I said, once you see what it factors to, it is obvious. But actually seeing that connection is rather difficult. The only thing I could recommend is you already know what you're working towards. You want sine of theta plus 1 over cosine of theta, which means you want to get rid of that sine theta plus cosine theta minus 1 in the denominator. So that should be a clue that maybe that's how it's going to factor. At that point, just check to make sure that's how it factors. Or, what color do I want to use? Or at that point, just say, okay, well, there's my left-hand side. Now try and get the right-hand side to be that form. And so kind of go. On the other hand, what was the right-hand side? Sine theta plus 1 over cosine. And go kind of the same game, say, oh, well, I know that I want sine theta plus cosine theta minus 1 in the denominator. So multiply numerator and denominator by that term, and then see what you get. I shouldn't have to go through that, right? Because I just showed you how it's going to factor, or what that was the factor form of, right? That's just going to be sine squared plus sine cosine plus cosine minus 1. Should we get a minus sign plus sign, which is 0? And then just look at what you got for the left-hand side. Are they the same? 99.9% confident that the test banks I use doesn't have anything this complicated. I'll put it this way. I've never run into anything this complicated in the test bank. So it's generally a good sign. Let's see if I can do this one. Oops, I didn't plus one. Looking at the wrong one. Minus secant theta plus 1. And here I kind of just notice, I want a tangent theta minus secant theta plus 1 in the denominator. So I'm going to force 1 in the denominator by multiplying by 1. And then just proceed from there. Let's see what we get. Tangent squared plus tangent minus secant squared plus secant. Is that what we're going to get? So it looks like you're going to get a minus secant tangent and a plus secant tangent, which will just be 0. Just double check that. Right, tangent squared minus secant tangent plus tangent. Plus secant tangent, there's the 0. Minus secant squared plus secant tangent. So that's what we should get. Now, how do I want to proceed? There's actually 2 ways to go. I'm going to go this way. Two ways, actually, right? I have a tangent squared and I have a secant squared. Pythagorean identity. 1 plus tangent squared is secant squared. Right?
Oh, yeah.
Or tangent squared is secant squared minus 1. So at this point, you could choose to either replace this tangent squared with a secant squared, right? So it'd be secant squared minus 1, or replace this secant squared with 1 plus tangent squared. You have to remember there's a minus there, so that minus gets distributed through. To avoid that negative, I think I'm going to replace that tangent squared. And I think that should get me right where I want to be. Let me do this just to show that that's what I replaced. I'll put those in green parentheses. Then we should see immediately that we're done, right? You get secant squared minus secant squared is 0. Then just rearrange your terms. We have tangent theta left over. We have that plus secant theta left over, and that minus 1 left over in the numerator.
Why is this secant squared? Why is secant squared 10 then 1 minus 1?
So about this one here.
No, the other way.
Over here.
No, yeah, that one.
Oh, I'm just rewriting. So this is just showing that all we did from here to here was replace the tangent squared.
That's the tangent. And then that one, that's secant squared.
Secant squared theta minus secant squared theta is 0, right? And then this is all you're left with. Yeah, so those two just wound up canceling out, right? That one was actually deceptively easy. After some of the ones we've been doing, that was very easy. That'd be like one of those test questions. You just had a bunch of hard test questions. Get this one on, you go, no, there's no way that was that easy. And then you overcomplicate it. That should be perfect. This homework only has 7 questions on it. There are no, unfortunately, verification questions. Those are actually really hard to do on an online homework system, right? So if I'm not mistaken, they're all things along these lines. Use fundamental identities to fully simplify. If I'm not mistaken, there's also questions like this. And write the trigonometric expression in terms of the given. Now, that one looks kind of fun to do. But doing these should still help you with verifying, right? Because it's still getting you practice using the identities and when to use them. So let's take a look at this one. Why not? Want to use the fundamental identities to fully simplify this expression. The first one I'm going to start with is to write cosecant in terms of sine, right? What's cosecant?
1 over sin.
Which is what? If we now simplify that. Right, sine over sine? Just one, isn't it? We're left with cosine of negative x. That is not fully simplified. Cosine is even. Cosine of negative x is cosine of x. That would be fully simplified. And just to check, let's come back over here. Oh, you're not going to let me type in the answer? Oh, that's annoying. Okay, well then. Oops, that's not it. Cosine x. Why is it not letting me type it in? Oh, I know why. It's not open yet. No, it should be open. Why is it not letting me? What's going on? Why is it not letting me type it in? It used to let me do that. Huh. I don't know why it's not letting me do anything. That's annoying. But that was right, that's on the backs. Because maybe I locked myself out something. That is really weird. Doesn't let me do that. Now it's letting me do it. I actually have to view it as a student. That's aggravating. Oh, let me find a good one. Let's try this one. So I'm going to simplify this in terms of just sine of x, which tells you how you should proceed, right? Write everything in terms of sines and cosines and see what happens. What's tangent?
Sine or cosine.
What's cotangent?
Cosine or sine.
And what's secant?
1 or cosine.
What is the LCD? Cosine times sine, right? You get what? Sine squared of x plus cosine squared of x all over just regular old sine of x. What's sine squared plus cosine squared?
1.
Should just get 1 over sine. And let's just verify that. 1 over sine of x. Okay. So again, really, best thing you can do is just do a lot of these types of problems. Just remember the methods. You can either start with one side, work to the other, reduce both sides so that they go to the exact same thing, or show that their difference is equal to 0. All 3 methods are valid. You are going to need your identities. So I'll repeat, all the identities we've gone over so far, you may want to keep them on a separate sheet of paper. Quick and handy. Starting tomorrow, Wednesday, we're going to be looking at your identities. So Wednesday are the sum and difference identities. So let me just go ahead and stop the recordings.